Okay, so speaking of data, I already showed you this figure, but I just want to spend a little bit of time outlining actually how we make this measurement and what this mass spectrum actually is. So this is a measure of the relative abundances, somehow, of these various isotopes of argon. And we're going to talk about what the different contributions to these is. So you already know that most of the argon-40, well, virtually all of the argon-40 is from the radioactive decay of potassium plus the atmosphere or something that's like atmosphere. The argon-39 comes mostly from potassium. Argon-38 comes from, and we'll be more specific about this, but argon-38 comes from both the atmosphere and from potassium, just like argon-39. Some argon-38 is made. Argon-37 comes, oh, and also chlorine. Argon-37 comes mostly from calcium, but some also comes from potassium, like 39. And that's really it, only two sources of argon-37. 36 argon comes from calcium and the atmosphere, principally, and chlorine also. So this should make you think a little bit. For example, if we're going to use an air correction for the argon-40 to determine how much of the argon-40 is radiogenic, I just told you that some of the argon-36 comes from calcium. So how are we going to figure that out? Important. So there are lots of complications that we have to keep in mind here. But one of the things I think you can appreciate now is a very important benefit of the argon-argon technique, which is that because we get isotopes like argon-37 mostly from calcium, argon-39 mostly from potassium, we can actually get compositional information about samples as well as age. If we do everything right, we can actually determine the ratio of calcium to potassium or of chlorine to either one of those from the argon-38 and 36 measurements. But we have to somehow separate out what the different contributions are. So that's really one of the goals of the next section here, is to decide how we determine that partitioning. So a little bit more about the mass spectrum and how we measure these things. What you should think of this spectrum as being is a qualitative relationship of the ratios of these different isotopes to each other. These are raw data. There are a number of corrections that have to be made before we can start doing what I just said, which is to determine the origin of each of these isotopes. And when I say qualitative, what I mean is that we would measure this peak as being the difference between the peak top, which we average in some way, minus this baseline value. So that peak height divided by this peak height is very close to the argon-40 to argon-39 ratio, but it's not exactly it. So we have to make some corrections, and I'll want to lead you through that. Because I really think it's important, when you read a paper that has argon-argon data in it, it's important to realize that there was a lot that went into that, and to some extent there's some things that can go wrong, so there's room for error. Okay, so what is this actually, how is this acquired? What does this spectrum come from? Well, there are a couple of ways in which one can scan through the masses in a mass spectrometer. And that's what I'm going to illustrate next. We don't need this, we already showed that. But first, let me just summarize the different corrections that we're going to be concerned with and that are necessary to go from this mass spectrum to the actual isotopes of interest. So we have to correct for background, and I'll go into more detail on these as we go through it. We have to correct for the background, or what we call the blank. We have to correct for discrimination, which is the selective bias that the instrument has for different isotopes. We have to correct for radioactive decay, because the two synthetic isotopes, argon-37 and argon-39, are radioactive and they decay, so we have to make a decay correction for those. And then we have to worry about what I called these interference corrections. For example, I mentioned that we produce some argon-36 from calcium, and if we want to make an air correction, we have to know how much of the argon-36 came from calcium versus the atmosphere before we can make a correction on the argon-40. So that's what I mean by interference corrections. So I want to try and explain all of these things in a little bit of detail, not a huge amount. Okay, so this is a schematic view of an argon-argon dating system, and it's composed of several components. This is a mass spectrometer. You can think of this as basically being three systems. The mass spectrometer is one, so this is where the isotopes are actually measured. The purification system, or what we call extraction line, is this region in here. And this region is devoted to taking gas that's created mainly by heating of a sample and purifying it so that we let only noble gases into the mass spectrometer. And then over here we have a sample chamber, which is some device for holding samples, and some way of heating the samples to release the gas within them. And in this case, in my lab, we use almost exclusively lasers to do that. Some people use furnaces to heat samples, but whatever the heating method is, gas can be released by heating, then it expands into this part of the system, and it's purified by reaction with various devices called getters. So these remove, for example, CO2, nitrogen, sulfur, etc. And all of the non-reactive gases remain, and they get let into the mass spectrometer. So this entire process is very easy to automate, so that you can, for example, turn on a laser to heat a sample, and the sample expands into this extraction line where it undergoes purification and eventually expands into the mass spectrometer where it gets analyzed. And this whole process can be completely automated so that you program a series of activities and let it run for days or weeks, actually, completely automated with no human intervention. So there are a lot of other little devices shown here, various pumps, turbomolecular pumps, vac ion pumps, and these act to pump out and clean out the system between each sample. Then there are pressure measuring devices, a thing called a cold finger, which is cooled to about minus 130 degrees centigrade to freeze out water and some hydrocarbon gases. So the whole purpose of this extraction system is to take the gas that you release from a sample and remove everything except noble gases, so helium, neon, argon, krypton, xenon, and then you analyze that. And the reason we want to clean the gas so extensively is because, well, there are really two reasons. One is because the more different kinds of gas you have in a sample, the more complex the mass spectrum becomes and dirty, and it becomes difficult to actually measure the samples. You also want to avoid having corrosive gases like sulfur or hydrogen chloride, HCl gas, in the mass spectrometer because it actually corrodes the instrument. So the purification is very important. And just to give you an idea of what the sort of throughput of this system is, typically if we're taking single crystals of, say, the mineral sanidine, which is very common, and heating them or actually fusing them with a laser, we would melt a sample and allow it to be purified for about 3 minutes. and then admitted into the mass spectrometer, and the mass spectrometry can take from, say, 30 minutes to 1 hour. So in more or less 1 hour, you have a complete analysis of a sample, which is really pretty short time. So one can generate a lot of data relatively quickly. Okay, now I just want to illustrate in a little bit more detail how the mass spectrometer works, because that's really the core of things. Basically, almost all of the mass spectrometers that are used for argon-argon dating, as well as for general noble gas geochemistry, are what are called magnetic sector mass spectrometers. And they have an ion source, which is typically a filament that basically bombards a sample of gas with electrons. That ionizes the gas, and then those ions are accelerated through a voltage, which is anywhere from 2 to 10 kilo electron volts. And those ions are then accelerated down a flight tube, and they are brought into the sector field of an electromagnet. Now, from here, there are really two different types of mass spectrometers. One has a single collector, and by changing the field of the electromagnet, or changing the current to the magnet, you focus one isotope beam at a time on the detector. So we would measure, say, in sequence, argon 40, 39, 38, 37, 36, etc., just by changing this magnetic field here. In a new type of machine, which has existed for about 5 years commercially, and is still going through some development, I should say, there are multi-collector mass spectrometers, where there's a different collector for each of these isotopes, and you get actually 5 different ion beams that you measure simultaneously. So this is still kind of somewhat experimental, I have to say, the multi-collection business. Most of argon-argon geochronology today, and probably for the next 5 years, is going to be done with these single collector machines. So the basic idea is ions are created over here, accelerated, and then separated by the magnet, and you focus one isotope at a time on the detector. So what that, oh no, I did that again. Here we go. What that produces then is data that look like this. So what we do is we change the magnetic field and measure a given isotope, and then we change the field to another value and measure another isotope, and so on. So these are several different kinds of samples here. This is a background measurement. This is an aliquot, or a measured amount of air argon, and this is an actual sample, but it could be a standard too. So what you see here is that we have the ion beam as measured in nanoamps, nanoamperes, as a function of time. And for these relatively abundant isotopes, here we measure first mass 40, then 39, then 38, then 37, then 36. And each of these little clusters of data has a number of different integrations. And you can see that they're tightly clustered for the stronger ion beams, and for the very weak ion beams, like argon 37 here, they're much more scattered. So the idea here is, because the ion beams behave differently, argon 40 and 39 are both falling, as is 38. But notice argon 36 is rising. So what we do is we extrapolate the data. We just fit a curve back to the time at which the gas was let into the mass spectrometer. And that's the fundamental datum that we measure to calculate the ratios. So this is just an example of how different data look for background measurements, where all the ion beams are very small, like argon 36 is here in this sample. All the ion beams are rising. The the bigger ion beams always fall. And that's a function of what we call memory in the mass spectrometer, because there's a lot of argon-40 that a mass spectrometer has analyzed over time. So anyway, this is what the fundamental data look like. They're just a bunch of measurements as a function of time, and we extrapolate those back to time 0. So that's what the fundamental measurement is. Now, with one of these multi-collector machines, instead of having these discrete clusters of data, each one of these would be basically a continuous curve. Now, one thing you might be interested in is to look at the time axis here. And this, let's take this one. This is 1, 2, 3, 4, 5, 15, 20, 5, 10, 15, 17 cycles. There's 17 clusters of data here. So this went through the cycle 40, 39, 38, 37, 36, back to 40, 17 times. So that's what that means. And you might notice there's a little gap here, here, between every 5. And that's because every 5 cycles, this instrument was programmed to recalibrate the position of the peak. And so it takes a little bit of extra time. So you see these gaps. What else can I say about these data? So the total time that it takes to go through these 17 cycles is, in this case, about, let's say, 1,500 seconds. Right? These are seconds. So that's 50 minutes, right? That's a pretty typical run for this number of cycles. With a multi-collector machine where you don't have to change the magnetic field all the time, and you measure all the isotopes simultaneously, you can get the equivalent amount of data in about 5 minutes. So it's much faster. But there are some problems associated with that too. And I don't think I'll go into that today. Okay, so these 3 examples, a background, an air pipette, and an unknown sample, or standard, these would be interchangeable, are 3 types of measurements that we have to make routinely. So when I say background or blank, what I mean is that when we analyze the sample, I'm going to go back here. You have to think about the process here. So when we fuse a sample or heat it to some temperature and collect the gas in this section and purify the gas and then let it into the mass spectrometer, while the sample is being heated and the gas is being purified, the mass spectrometer over here is open to a pump, which continually pumps on the mass spectrometer to keep the background low. So we basically pump on the mass spectrometer all the time until we're ready to let the gas in. So as soon as we let the gas into the mass spectrometer, a valve here opens and a valve here to a pump closes. And after that, what happens is there's some gas in the mass spectrometer that is always there, and as soon as you stop pumping on it, it starts to actually increase because it desorbs from the walls of the mass spectrometer. So we have to correct for that, and that's what this blank measurement is. So this is gas that's in the system, and whenever we analyze a sample, this is here too. So we have to measure this every now and then and know how much background there is that has to be subtracted. So this is an air pipette, which is about 0.2 cc's of purified atmospheric argon. So why do we analyze that? I'll come back to that in a minute, but we need to use this to determine the bias in the isotopes. Sometimes it's called mass discrimination, sometimes it's called mass fractionation, but we need to measure it for a material that we know very, very well, and atmospheric argon is extremely well known. So we have to analyze these kinds of samples now and then. And notice we're only measuring 3 isotopes here, argon-40, 38, and 36. And 38, as you can see, is extremely scattered because it's very, very low in abundance. So that's why there's only 3 isotopes measured here. Okay, so that's what data look like, the real fundamental data. And basically, I'm just going to go through what the arithmetic looks like for each of these kinds of corrections. So for a blank or background correction, we take the measured value of isotope I, whatever I is, and subtract the blank that we measure, and that's the value that's corrected for C means corrected and B means corrected for blank. Very simple. Now the discrimination correction is a little bit trickier. And here, what we do is we suppose that the measured value that we have now corrected for blank is still not the correct value because the process of ionization of argon may favor heavier isotopes or lighter isotopes. We don't really know all the time. And the detection of those ion beams may favor heavier or lighter isotopes. And we can't distinguish between ionization bias versus detection bias. All we know is what the final result is. And so we say, okay, the true answer is equal to the blank corrected value times some discrimination. We'll just call this discrimination for mass I. And based on lots of data for air pipettes and various other samples, we actually understand that for the mass spectrometers in my lab, the discrimination correction, or that number D, follows a power law. So that for an isotope, let's say, we can take any one of these isotopes as the normalization basis. And if we start with argon-36, let's say argon-36 is the basis, so we don't make a correction for that. We say that 1 mass difference means you multiply by just D. 2 mass difference, you multiply by D squared, and so on. So this is why we call it a power law correction. And so then the question becomes, given that we know what the mathematical relationship is, or at least this is the best approximation that we can determine, how do we actually measure this number D? And I'll mention now that this power law relationship is not necessarily always true for all kinds of mass spectrometers measuring argon. Some different kinds have a linear relationship. Some seem to have an exponential relationship, and that has to be worked out for each individual mass spectrometer. So how do we measure this value D? Well, this is why we measure air pipettes. So we say that the argon-40-36 ratio of a discrimination corrected air pipette value should be equal to the ratio that we measure times D to the 4th, since we have a power law, and then we just solve for D. So it's the 4th root of the atmospheric ratio divided by the ratio that we measure. So it's pretty straightforward. Just to give you an idea, we often measure in my laboratory on, we have 3 different mass spectrometers that are used for argon-argon dating, and they all have their own extraction lines. And on all of them, the argon-40-36 ratio that we measure for an air pipette is usually about 292, not 298.56. So that corresponds to a D value of about 1.005, more or less. So that's the magnitude of the correction that has to be made, just to give you an idea. And to reiterate, this correction is a function of both the detection and the ionization. We can't tell which is which, but somehow the sum of those 2 processes seems to favor the lighter isotope, argon-36. So that's the discrimination correction. Oops. And then finally, we have to do the decay correction, which I mentioned earlier is needed for both argon-39 and 37. And you'll notice that these are given in terms of decay constants. So the half-life corresponding to each of these is, if you remember the formula, which is the natural logarithm of 2 divided by this. For argon-39, it's 269 years. So argon-39, between the time that we irradiate a sample and the time that we analyze it, doesn't really change by very much. So this decay correction is pretty small. For argon-37, this decay constant translates to a half-life of 35 days. So essentially, every month after we irradiate a sample, the argon-37 decreases by a factor of 2. So if we wait 4 months, we're getting down there. 16 times less abundant than it started with. And basically this means that after a year or so, you cannot measure the argon-37 at all. It's just gone. So why do we care about argon-37? Well, we'll come back to that, but it is important for certain kinds of samples. So the decay correction is pretty straightforward. It's simply given by these formulas, which are somewhat simplified because this assumes that the irradiation was instantaneous and that the length of time between the irradiation and the analysis is long compared to the duration of the irradiation. Now, in fact, I mentioned to you that various nuclear reactors, and in particular the Oregon State one that we use, only runs for 7 hours a day, 5 days a week. So if we want to irradiate a sample for 300 hours, it has to be done in many discrete times. And so the decay correction gets a little bit more complicated than this, but it's possible to do. And the mathematics is just a little bit more complicated, but this communicates the basic idea. So the decay correction has to be done too. Now you might well ask, I've just given you 3 different kinds of corrections that we have to make to the raw data that we measure. Blank correction, discrimination correction, decay correction. Do you think it makes any difference which order we do this in? I hear some very quiet yeses. It does, yes. Those yeses are correct. But the difference between when you make the blank correction or the discrimination correction generally is unimportant. You can do those in either order. But the decay correction has to be done after those. And the reason for that is because if you decay correct the background, you'll get ridiculous numbers because the background is essentially 0. And so you can have very large fluctuations. So you don't want to be decay correcting a background and then subtracting the background from the sample. So the blank and the discrimination correction can be done either way. Either one can be done first, but the decay correction has to be done after those two have been done. Does that make sense? Okay. All right. So now let's get into this business of where the different isotopes come from. And this is a chart showing essentially all of the reactions that happen in a reactor from target elements of chlorine, potassium, and calcium. So these are the nearest neighbors of potassium in terms of atomic mass. And the shorthand, or the symbology here, is let's use this one as an example. So this is a reaction where potassium 39 is the target isotope, and a neutron is absorbed because this is a neutron-producing reactor. So these are all neutron-in reactions, as they're called. And then the products that are produced are shown to the right of the comma. So neutron in, neutron, and deuteron out. So deuteron is hydrogen with two neutrons, and a neutron is a neutron. So if you add up all the neutrons and protons, you'll see that that makes argon 37. The reaction that this is all about, the one that motivates us to irradiate the samples to begin with, is this one. Potassium 39, neutron in, proton out, gives you argon 39. So what I've shown here are the reactions that are beneficial, that we actually derive some benefit from, are shown in green. And the reactions that are bad, that we don't like, are shown in red. So let me explain why. This reaction, this is a kind of an interesting one, because chlorine, which has two isotopes, 35 and 37, absorbs a neutron and emits a gamma ray. So there's no nuclear reaction involved there, except that you increase the number of neutrons. So this neutron is absorbed and it turns into chlorine 36, but chlorine 36 is radioactive. So then it decays to argon 36 with about a 300,000 year half-life. So we make chlorine 36 very quickly, immediately, and then that chlorine 36 decays to argon 36 on a time scale that's basically irrelevant to the laboratory. 300,000 years is just insignificantly long for us. But another reaction that produces argon 36 is this reaction on calcium, and this is one that I mentioned earlier. So calcium 40 absorbs a neutron and emits both a neutron and an alpha particle, which you remember probably is 2 neutrons plus 2 protons. So it emits basically 3 neutrons and 2 protons and becomes argon 36. So this one we really do have to worry about because this interferes with the air correction if we choose to make an air correction. But fortunately, we also have a reaction on calcium 40, which gives us argon 37. And here it's just a neutron absorbed and an alpha particle ejected, so one less neutron than this one, to give us argon 37. So now if we know the ratio of argon 36 to argon 37 that's produced from calcium, we can make a correction for that. In other words, if we take the 36 to 37 argon ratio that's produced from calcium, and we know that it's produced from calcium 40, but that doesn't really matter, we can take the argon 37 that we measure and multiply it by that production ratio and subtract the result from the total argon 36 that we measure and say, okay, the rest is atmospheric. To a first order, that's a good approximation, assuming that we can neglect this reaction, which means that we analyze our sample within decades of when we irradiated it, which we always do, because if we don't, this will all be gone, and our ability to make this calcium correction disappears. So let me ask this. What kind of samples, which minerals, geologically speaking, would you expect to produce a lot of argon 37? What minerals have a lot of calcium in them? Plagioclase, certainly. Another one? How about a hydrous one? Yeah, right. So plagioclases and amphiboles, we produce a lot of argon 37, and that means that this correction becomes more important for those. So in turn, that means two things. We want to analyze the sample relatively soon after irradiation, but not too soon because we don't want too much argon-37. And I'll tell you why. It's because argon-37 is so radioactive that it decays on the detector, and the detector can't distinguish the decay events from ions being measured. So you increase the background, basically, for argon-37, and you don't want to do that. So you have to be very careful about how long after the irradiation you analyze the sample, if it has a lot of calcium in it. And one way that we minimize this correction, the magnitude of this correction on argon-36, is to under-irradiate the sample. So in other words, given that we have some tolerance, we can measure some range of isotope ratios, and there's an ideal length of time for any age sample. There's the perfect time for irradiation is the time that gives you an argon-40 to 39 ratio of 1. That's the ideal. But if you anticipate having a very large calcium correction, you would irradiate for less than that, for less than the amount of time that would give you a 40-39 ratio of 1. So there's a lot of thought that has to go into how long you irradiate samples for these kinds of reasons. Okay, another important bad reaction is this one shown here. So this is kind of the analog of the good reaction, an NP reaction, except that instead of potassium-39 as the target, potassium-40 is the target. And it's a neutron in, proton out reaction that gives you argon-40. So the reason this is a bad reaction is pretty obvious. It's argon-40 that we're really interested in. So if we don't know how much argon-40 we produced from potassium in the reactor, it's very hard to know how much of the argon-40 is radiogenic, even if we make the air correction. So the good news is that we measure the argon-39 from potassium, and because the ratio of potassium-39 to potassium-40 is constant within that 0.6% tolerance, the ratio of argon-39 to argon-40 that's produced in the reactor is also constant. So again, just like with the argon-36, we can make a correction for this. In other words, we can measure the argon-40 to 39 ratio from potassium and take the argon-39 that we measure, multiply it by that ratio, and that gives us the amount of argon-40 that comes from potassium, and we just subtract that from the argon-40. I'm going to go over again exactly how these corrections are made, but I just want to give you a basic idea here. So another reaction that's bad is this one, an N-alpha reaction on calcium-42, which produces argon-39. Well, the argon-39 that we want is really from potassium. So any argon-39 we get from calcium is not good. But we can do the same thing, measure the argon-37 from calcium, and take that ratio and subtract it from the argon-39. But notice that here we also get some argon-37 from potassium. So it starts to be very confusing. You start to wonder, well, can we actually can we meaningfully understand which target elements each of these isotopes come from? Is there any hope of doing this? So right now you're supposed to be very sad and depressed and think this is hopeless. But obviously it's not. But just to emphasize that there's a lot of stuff going on in the reactor that we have to keep track of. And finally, another reaction. By the way, the reactions that are just shown in black are typically the production rate is very, very, very low. And so for the most part, these things can be either ignored or are easily corrected for. It's just the most important bad or good ones are shown in colors. I'm showing this reaction. So just as there's a reaction on chlorine 35, the other isotope of chlorine has a totally analogous reaction. It goes to chlorine 38. But then the decay to argon 38 is effectively immediate. I think the half-life is hours, 2 hours or something. So by the time you actually analyze the sample, all of the chlorine 38 has decayed to argon 38. And the reason I colored this green is because this gives us information about chlorine. So we get the compositional information from the sample. 37 gives us calcium, 38 gives us chlorine, 39 gives us potassium. And this turns out to be very, very useful for diagnosing things like alteration in minerals, zoning, lots of different effects can be. It's very nice to have this compositional information. Okay, so I guess the only other thing I wanted to mention here is that I had emphasized that we can measure these production ratios and make corrections based on them. Well, how do we do that? Well, what you want to do is take a sample or a material for determining the 36 argon to 37 argon production ratio from calcium. You would want a material which has calcium in it, obviously, and nothing else. Because if you have any potassium in it, you might get, you might get some of this, argon 37 from potassium. Similarly, for measuring the argon 40 to 39 ratio, you would want a material that had no calcium in it. So we take pure salts, for example, to measure the isotope production ratios from calcium, we use the mineral fluorite, calcium fluoride, CaF2, synthetic so that it has no impurities, and that's the material we use. For measuring the potassium production ratios, we make a synthetic glass. It has the composition of calcilite, which is KAlSiO4, but it's glass, so it's easily fused. And for the chlorine production ratios, we use halite, or synthetic halite, just NaCl. So these are things that have to be measured along with standards and air pipettes periodically. But the question is, well, how often do you need to measure these? Do these production ratios vary? Do they vary between one irradiation and another one? Do they vary at different places within a reactor? So I showed you earlier a package of samples with a bunch of standards. Do we have to worry about variations in these production ratios within a given irradiation? These are important things to know, so we have to measure them periodically. It turns out that for a given reactor with a given fuel, and the fuel is highly enriched uranium, so it's uranium that's been purified to have a very high U-235 to U-238 ratio. As long as the fuel is the same in the same reactor, these production ratios seem to be very constant. We cannot tell the difference from one irradiation to the next. So we do measure them periodically, but not in every irradiation. A couple of other points here. One expects in particular that the correction for the argon 36 to argon 37 ratio from calcium is especially uniform, and you expect it to be uniform because those are both derived from the same isotope of calcium, both from calcium 40. Now, notice that argon 39 produced from calcium comes from mostly from calcium 42, a little bit from calcium 43 by this reaction, but this is very, very small. In fact, we usually can't even detect this. So this is coming from a different isotope of calcium. So if our samples have a different calcium isotopic composition than the fluorite that we measure, we might have problems, right? You see that? And we also know that calcium 40 comes from the beta decay of potassium 40. So if our synthetic fluorite happened to be made from some calcium that was highly radiogenic, that was derived from some Precambrian shield or something, we might expect to get a different ratio of argon 39 to argon 37 than in a sample, say. We've never seen any variation, so that concern is theoretically something to consider, but it doesn't seem to be a problem. The other thing I want to mention here is that we can actually control some of these reactions. So this one in particular is one of the bad reactions because this gets confused with the radiogenic argon 40 that we're trying to measure. Well, it turns out that this reaction is mostly driven by neutrons with very low energy. Low energy, I mean less than 0.1 MeV, mega electron volt energy. Whereas this reaction is mostly driven by neutrons with energies greater than 2 MeV. So if we can somehow filter out the low energy neutrons, we can minimize this reaction. That means we can minimize the correction, which minimizes the error that we have to propagate through the whole age equation. And the way we can do that is to use shielding. So we take this can of samples and put it inside of a container made of a material that absorbs low energy neutrons. And also, well, the other reaction that's driven by very low energy neutrons is this one. So if we use this kind of shielding to minimize production of argon 40, we lose the ability to determine the chlorine isotope or the chlorine in a sample. So we lose compositional information. There's a trade-off. But to do this, we routinely use the mineral cadmium, or the metal cadmium. Cadmium has a very strong absorption for these low energy neutrons. Other materials work too, gadolinium, for example, but gadolinium is expensive compared to cadmium. So some reactors, including the one in Oregon, have a special facility that has a cadmium lining, and you put the samples in it, so you minimize this reaction here. And unfortunately, you minimize this one too. But typically, if we have a mineral like, say, hornblende or biotite, which tends to have a fair amount of chlorine in it, we usually get enough that we can still measure it and derive this kind of information. Okay, I think that's really all I wanted to talk about here. Any questions before we move on? Yeah. Yeah, that's a very good question. The blank correction can be the most important correction. In fact, it usually is. But it depends on how big the sample is that you're measuring, and to some extent how old it is. The blank usually has, let me go back to that. Oops. So here's this typical blank, and it's kind of hard to see here because these numbers are not very big, but the argon 40 blank is the highest in this, of all these isotopes. And the next highest is 39, and the next highest is 36. And the least abundant are the 37 and 38. So for samples that are very small and or very young and or very low in potassium, so that the argon 40 signal is very small, the argon 40 blank can be very important. And sometimes Sometimes we measure samples that are only 5 times the background. And that means that the uncertainty is very large. I mean, can be 25% or more. So the background correction is usually the most important one. Yeah, that's a very good question. But most of these corrections, the importance of the correction is really dependent on the sample. So I can't say that any single one of these corrections is the most important for all samples. It depends on the age, the composition, and the amount of sample. Okay, so there's this whole wealth of isotopes that we produce, and somehow we have to make sense of this. Well, we can write down now all the sources for each of the isotopes. So argon-40 is composed of the radiogenic argon-40, which we hope is the biggest by far. Some of the argon-40 is from the atmosphere, so A is air. And some of the argon-40 is produced from potassium by that reaction that I mentioned. Argon-39 is pretty simple. It's only produced from potassium and calcium. Argon-38 is pretty complicated, more even than 40, because we have an atmospheric component. Some derive from potassium, some derive from calcium, and some derive from chlorine. Argon-37, like 39, is very simple, only from calcium and potassium. And argon-36 is atmospheric, calcium, and chlorine. So you can see that the sensitivity of different samples to these corrections depends strongly on the composition. And for example, the mineral that is most desirable for doing high precision geochronology of volcanic rocks is sanidine, because it has such high potassium and typically very low calcium. For sanidine, almost without exception, you can completely ignore this argon-39 contribution from calcium, because the calcium is just so small. But if you irradiate the sample too long, you may generate enough argon-39 from calcium that it becomes significant. So this is one of the reasons why you have to be careful about how long you radiate samples. Also for sanidine, probably you can completely ignore the chlorine-derived argon-38 or 36, because sanidine has essentially no chlorine. But here you have to really, I mean, we don't actually have to ignore these things. But in some cases, it's sort of useful to do that. But you have to keep track of the fact that any mineral may have inclusions of other minerals. So for example, in sanidine, you may well have inclusions of apatite. This is very common. Or melt inclusions, or even fluid inclusions, vapor inclusions. And any of these inclusions can contribute isotopes that are not part of the actual mineral that you're trying to analyze. So even at the single mineral scale, there are heterogeneities that you have to worry about. Yeah, okay, so this is a list of all the sources of these different isotopes. And this might appear hopeless. You could say, well, what I have here is 5 equations in, I haven't even counted, but probably 15 unknowns. So you can't possibly solve that uniquely for each of these different contributions. But this is where these production ratios come in handy. Whoops. So we can take the same equations and say now that, for example, the argon-40, the argon-40 from the atmosphere, which is what this term is equal to the argon-36 from the atmosphere times the 40-36 ratio of air. And similarly, you can say that the argon-40 from potassium is equal to the argon-39 from potassium times the 40 to argon-39 ratio you get from potassium. You see? So this reduces the number of unknowns significantly. So we have to measure the production ratios of argon-40 to 39 from potassium, of 38 to 39 from potassium, and 37 to 39 from potassium. And for atmosphere, we have to know the argon-40-36 ratio and the argon-38-36 ratio. And from calcium, we have to know the argon-36-37 ratio and the argon-38-37 ratio and the argon-39-37 ratio. So we can measure all those ratios. And from chlorine, we have to know the argon-36 to 38 ratio. So we can measure all of the ratios we need by measuring 3 samples, one that has only chlorine in it, one that has only calcium in it, and one that has only potassium in it. And as I mentioned before, we do this, let's say, every 10 irradiations or so, and we can never tell the difference from one to another. So that seems pretty secure. So we basically just use the average production ratios to make these corrections. So now, I don't know if anybody's counted, but just by magic, it turns out that this reduces to 5 equations and 5 unknowns. Very nice, huh? So we can basically write a matrix, invert the matrix, and we have a unique solution for every single one of these fundamental parameters that we need to know. So once we solve for these, this argon-40 radiogenic to argon-39 from potassium ratio, which is the fundamental part of the age equation, is ours. If we have correctly estimated that all of the non-radiogenic and all the non-potassium-derived argon-40 is atmospheric. So that's still an issue. We haven't conquered that yet. Okay, so I just want to give you a feel for the magnitude of some of these corrections, and in particular this potassium correction. So this is from the argon-40 that's produced from potassium. And what I'm showing here is the magnitude of the correction in thousands of years as a function of what this ratio is in the reactor. And if you look at all the reactors in the world, the range of production ratios of argon-40-39 from potassium encompasses this whole range. And the reason why this range is so large is because it depends on the energy spectrum of the neutrons in the reactor. It depends on the ratio of the relatively high, or actually, in this sense, it depends on the ratio of low energy neutrons to high energy neutrons. And that ratio is determined by the kind of fuel that's used in the reactor. It's partly the geometry, what else is being irradiated that absorbs different kinds of neutrons, and so on. So obviously, the more of this argon-40 you produce from potassium, the bigger the correction will be. And also shown here is the amount of this correction as a function of duration of the irradiation. Right, so this line here shows the range of ratios that you will get in this cadmium shielding environment, which is routinely available in the Oregon State reactor and in some other reactors. So this means that for the same 1 hour irradiation, even if we don't make a correction, we only introduce about 20,000 years of error. Which, I say only. That can be big if the sample is 20,000 years. That's a big correction. So this is why we have to really understand these corrections and make them as precisely as possible.